Okay, this is part 2. We'll see how this goes. Going to try to wrap this up in this section. You'll know if I didn't, though. So we're into the point where we now have some inverse trig functions. We're finding derivatives of those. On this test, I'm going to go ahead and give you these formulas. You'll have access to these, and that should be helpful. It's just that inverse trig derivatives just don't get used a whole lot moving forward. If I find out that this is something we definitely need to know for the AP test, we will take the time to learn them and make certain we know them at that time. Bottom line, we did go through the process of deriving these, so if you're stuck, there is an avenue to derive them, but you're going to be given those for this test. So we're to find the secant's derivative. Pull this right back up here one more time. Secant, cosecant are kind of the biggest mess. One thing to note, it does switch from sign from 1 minus u squared to u squared minus 1 under the square root, and we got this little absolute value thrown in there. So secant's derivative wants to be 1 on the absolute value of the argument, so this is actually dy ds, not dx, wants to be 1 on the absolute value of the argument, 2s minus 1, and I'm going to beg you, do not let your absolute value sign look like a 1. So I don't want this to look like a 12, I don't want this to look like a minus 11. And then we take that times the square root of the argument, 2s minus 1 squared minus 1, and then we multiply that by the inside derivative. We can either multiply that out here, or we can say times the inside derivative. The inside derivative is 2. So we get, all looks fine, we get 2 on absolute value 2s minus 1. And then we look, is there some benefit perhaps to foiling this? And absolutely there's a benefit to foiling this, because when I foil this, I'm going to get a plus 1, cancel that 1, then we'll see what happens from there. 2s, I'm going to get a 2s times 2s, or a 4s squared. In foiling, I would get a minus 2s and another minus 2s minus 4s. I would get a plus 1, but minus 1. And now we're at a point where hopefully we're being led down the simplification highway here. Yes, I should simplify because there's a cancel there, but now I have a factor of 4, and s if you like, but most importantly I have a factor of 4 that I can pull out of this square root, and it becomes a 2, and the 2 cancels the 2. So dy, let me come all the way down here, dy ds, it's derivative of y with respect to s, is if I pull that, if I make this factor become 2 times square root of s squared minus s, 2's cancel, and I get 2 on. How about this absolute value? Sometimes we can cancel the absolute value, but 2s minus 1 could be a negative number, so it stays in play, 2s minus 1, but I'm left with, oh shoot, and I canceled that, sorry, that should be a 1, and I'm left with just the square root of s squared minus s. Okay, let's move on from there. That's number 10. Number 11. We're now finding another derivative. Truthfully, since we got the formulas on these, we should get through these, provided we get through the simplification. And sometimes there's a fair amount to do once we're done with just the derivative process. So dy dx y prime, I would finally answer that with dy dx. Cosine inverse. Cosine, negative 1 on square root, 1 minus the argument squared. So it wants to be negative 1 on square root, 1 minus the entire argument squared. Man, it's really easy to do this. Go 3x squared, but it's the entire argument squared. Then times the inside derivative, I'm going to go ahead and put it out here this time, times 3x's derivative, 3. So I get negative 3 on square root 1 minus 9x squared. Any simplifying there? Oh, we're in luck. Dy dx is negative 3 on big square root 1 minus 9x squared. Nothing we can do about that. You can say, well, we can factor this. Yeah, we could make this 1 plus 3x times 1 minus 3x. Any payoff? Okay, number 12. Tangent inverse. Tangent and cotangent are my favorites. Tangent, 1 on, 1 plus the argument squared. So this wants to be 1 on, 1 plus the argument, all of it squared. So we're going to have a little bit of simplifying to do on this guy. I get 1 on, 1 plus 4 on x to the 4th. I would multiply by x to the 4th on x to the 4th, and we get x to the 4th on x to the 4th plus 4. I do not want compound fractions as our answer, so dy dx is x to the 4th on x to the 4th plus 4. Do I need to say it? I'll say it. Don't you dare think about canceling those. X to the 4th is a term. You're calculus students, not algebra 1 students. Okay, so there's a quick page for us. Let's take a look at number 13. If I can get my hands on it. Now we just have a whole series of derivatives where we're just going to throw a bunch of what could be fairly simple problems at you. There's not a whole lot of space provided, so let's see how it goes. The derivative of e to the, I just call this the e to the rule. The derivative of e to the just wants to be e to the, but we have an inside function here, negative 4x. So dy dx, or y prime, wants to just be e to the negative 4x, but now we need to find the derivative of this guy. That's times negative 4, and this would be best answered as negative 4 e to the negative 4x. dy dx, x to the root 3, we say, well, I don't know, is this some kind of inside, x to some inside function? No, not at all. This is just a constant number. Square root of 3, it's 1.7-ish. If this was plain old 6, I'd say it's 6x to the 6 minus 1. So y prime is, we'll see if we have any simplifying, square root of 3 times x to the square root of 3 minus 1. Now, possible that we would think of this as a square root of 3 times another x to the negative first and put the x in the denominator. So this actually could look like, if you were doing a homework problem, this actually could look like, excuse me, I'll put it over here, it could look like square root of 3 times x to the root 3 times x to the negative first. You see how that would be the same as this? And then we could get root 3 x to the root 3 all on x, but I don't see that as being anything preferential to this. dy dx is root 3 x to the root 3 minus 1. Okay, 5 to the x. All right, we have a rule for e to the x. E to the x, the derivative just wants to be e to the x. Baby derivative. 5 to the x wants to be like e to the x. So it wishes it could just be dy dx equals 5 to the x. But it's not e, so we compensate for that by multiplying this by ln of the base, 5, and now times inside derivative, but inside derivative is just 1. So we get 5 to the x, ln 5, nothing to it. And now we're going to combine some things into product rules. Product rule, function of x times function of x, product rule. So I'm going to need some space here. So y prime, or dy dx, is the first function, e to the x, times derivative of the second function, plus the derivative of the first function. Well, derivative of e to the x is e to the x, times the just plain second function. Just plain second function, come on, x to the second. Minus, I'm going to put this in parentheses, product rule. Plain old first function, I'm going to call 2x, times derivative of second, that's still e to the x, plus derivative of first function, 2, plain old second, e to the x, which is a little bit disconcerting because it looks like we did the plain old second twice, but this was actually the derivative of this. This was actually the derivative of the second right here. Derivative of e to the x is e to the x. So we get e to maybe 2e to the x plus e to the x squared minus 2, I'm going to rewrite that in the same order as this, e to the xx, minus 2e to the x. So I see that these guys cancel. These don't combine, so I get e to the x squared, or x squared e to the x, take your pick, minus 2 e to the x. Pretty quick page here. Okay, find dy dx. Not a product rule. This is not ln times. ln by itself has no meaning. It has to be ln of something. It's ln of this. This is a chain rule. So derivative of ln. Derivative of ln of x is just 1 on x. So the derivative of ln wants to be 1 on the argument. So y prime wants to be 1 on 2 plus sine of x, but we've got an inside function, so the inside derivative is cosine of x. We get cosine of x on 2 plus sine of x. No, you don't need to ask. We do not treat that as cosine on sine and call this cotangent. Sine is not a factor of the denominator. So that is it. We've got dy dx. Ooh, I didn't put it on some of these others. I hope you were yelling at your computer. Come on, Mr. Hearn, we need a dy dx there. You tell us that all the time. Dy dx, that's what they're asking for. Dy dx equals cosine of x on 2 plus sine of x. This is our some of this is our 4-4 material. 4-4, one of the easier sections in the book, the rest of the way running. Okay, gets us to number 18. Find the derivative of this. Well, that looks pretty simple. We've got a rule for x to the something. We've got a rule for a plain old number to the x, but we don't have a rule for a function of x to a function of x. So here's the big hint. Use logarithmic differentiation. I'm going to use logarithmic differentiation for this. There actually is a rule for the function of x to a function of x, but it really is just one. You're only one step away from logarithmic differentiation when you do it. Maybe we'll talk about that, but the rule we could apply here directly is the same rule that we're going to be using here. Let's take ln of both sides. So I get ln y equals ln x to the x, and the payoff for that is ln y equals x ln x. I can pull that exponent out in front, and now if I take the derivative of ln wants to be 1 on, this is 1 on y, but dy dx equals product rule, that's x times derivative ln x, 1 on x, plus derivative of x, 1, times plain old ln x, or I get, I'm going to leave a blank here, you'll see why, I get 1 plus ln x equals 1 on y dy dx. But I don't want 1 on y dy dx. I want dy dx alone. So I would like to multiply this side by y and the other side by y, but if I multiply this side by y, I'm just muddying up the water. I want x's over here. So if I multiply this side by y and this side by x to the x, I'm multiplying both sides of an equation by the same thing. So dy dx is x to the x, and you could distribute that if you want, but I'm going to leave it 1 plus ln x this way. No, that's one of those cases where what have we really accomplished here? Nothing really reduced. I'd say that's fine. Okay, use logarithmic differentiation. Well, we know how to do that. We just did. What's the payoff? I might want to think of this as x times x squared minus 1 to the 1/2 time, or divided by x plus 2 to the 1/3. Okay, ln y equals ln of x squared minus 1 to the 1/2 all on x plus 2 to the 1/3. But what we know about logarithms is if everything is a factor, like x is a factor of the numerator, x squared minus 1 to the 1/2 is a factor, x plus 2 to the 1/3 is a factor of the denominator, all of my factors of the numerator become positives, so this is ln x plus ln x squared minus 1 to the 1/2, and in the denominator minus ln x plus 2 to the 1/3. Okay, that's all right. I haven't even started taking derivatives yet. How about we pull out this 1/2 and I get ln x squared minus 1 minus ln, oh, should put a 1/3 out in front of here too. I bet you caught that. X plus 2. And now how about I take the derivative of? The derivative of ln y, it wants to be 1 on y, but chain rule says I have to take derivative of y with respect to x still. Derivative of ln x, 1 on x, plus 1 on 2. Derivative of ln of x squared minus 1. X squared minus 1 is 1 on x squared minus 1 times the inside derivative, 2x, times 2x. Minus 1 on 3. Derivative of x plus 2 is 1 on x plus 2 times x plus 2's derivative, but that's just 1. So I get, I'm going to leave a blank here, 1 on x plus 2's cancel, x on x squared minus 1 minus 1 on 3 times x plus 2 equals 1 on y dy dx. But I don't want 1 on y here. I'm going to multiply by y. I could multiply this side by y, but I would rather multiply this side in terms of x. So final answer, dy dx, is this original big mess. That's my y value. Times 1 on x plus x on x squared minus 1 minus 1 on either 3x plus 6 or 3 times x plus 2. I'm not on that problem going to ask for common denominators. That's a pretty clear representation of our answer. So that's what your last problem on the test is going to look like. Good luck, stay tuned, and use Uniball Signos. They're the best.